All right, so today we're going to do 8.3, which is about applications. As a heads up here, I would expect to see a homework quiz at some point this week covering sections 1 and 2, just converting back and forth between your different vector forms and doing vector operations. So as a heads up, you should probably expect to see that one day this week. All right, so the main type of application that we're going to be looking at in this section are going to be these navigation type problems. So these will all resemble kind of a story problem. So let's just kind of work through an example, talk about how the vectors kind of come into it. So it says here that a boat leaves a port and averages 40 knots, that's nautical miles per hour, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? Okay, so one little definition piece that we need to come in or talk about before we start is this idea of bearings. So when we do a bearing, all bearings start relative to north. And we're going to, when we do a bearing, we're going to be rotating clockwise. So 215 is 90, 180, and then like 35 more. Hi, Joey. Is everybody okay with this idea? So bearings, we start at north, and we always go clockwise. So that's just like a little aside. Before I start the problem, we need to talk about what a bearing is, how to measure it, Okay. So far, so good? All right. So to do this problem, I'm going to start by looking at my two parts. So I have a boat at a speed, a time, and a bearing. And then I have the same boat with a new bearing, a new speed, and a new time. So the first thing I'm going to do is I'm going to give these two different legs of my journey a name. So I'm going to say that the yellow is going to be U and the green is going to be V. And I'm going to use a vector quantity to represent these. And my first order of business is going to be to resolve that information into a magnitude and a direction for each vector U and V. So I'll start with my U. So it tells me that my bearing is 215. But I don't want my vector described with its direction described with a bearing. I want a trig angle. I want a standard position angle so I can do sine, cosine, and tangent with it. So my trig standard position angle starts at the positive x-axis and goes counterclockwise. So that's the actual direction I want. So that's going to be 90, and then 90, and then what's the leftovers there in quadrant 3? It's got to be 55, right? How'd you get 55? 90 minus 35. Everybody's okay? So we're going to say the direction for U is going to be 235. 90 plus 90 plus 55. So far, so good. Now I want to come up with the magnitude. So the magnitude is going to be basically how far the thing is. So we're going 40 miles per hour for 2 hours. So how far did we end up going? $80, right? 40 miles per hour for 2 hours is 80 miles. Everybody agree? Okay. So far, so good. I'm going to do the same thing then for my vector V. So again, we're doing a bearing, and my bearing was 162. So again, we start at north. There's 90, and then like 72 more. But we don't want a bearing, we want a trig angle. So that would be 90 plus 90 plus 90 plus 18. or 288. And my magnitude for V, we said we went 55 knots for 3 hours. So that's 165. So now I have the information that's given to me translated into vectors described as a magnitude and a direction, right? My next step then is going to be to resolve these vectors into component form. Do you remember the formula to change a vector from magnitude and direction into component form? So it doesn't have a square root in it. That formula is the magnitude times cosine of the direction, comma, the magnitude times sine of the direction. That's just okay. Component form means it's the notation with the wedged brackets. So if we do that, we're going to have 80 times cosine of 235, comma 80 times sine 235. And we'll go to our calculator here and compute that. Before I start, though, I want to make sure that my calculator is in degree mode. So I've gone ahead and going to press the mode button, make sure I'm in degree mode. I know I need to be in degree mode because all the angles are described using degree symbols. So I'll do 80 times cosine of 235. And then I'll do 80 times sine 235. So I get, let's say, negative 45.9, comma, negative 65.5. So far, so good. We'll do the same thing now for vector v. So 165 cosine 288, comma 165 sine 288. And then go to my calculator once again. So I have, let's say, 51.0 and then negative 156.9. Good. Hi, Tommy.
Hey, school.
Come on in. Find a spot. So far, so good. Okay. Now let's think about what it is that we're really being asked for here, right? So I have my boat. It does that. And then we change directions. And we kind of do that then, right? What we're being asked for then at the end is about this vector. We'll call that guy vector R. R for resultant. So if I know the length of that vector R, that'll be how far the boat is from port. If I know the direction for vector R, I'll know what direction it lies from port. So my next goal is going to be to come up with this vector R. Based on the picture I've drawn, how do I compute vector R? Notice that I've written the vectors u and v, head to tail. That should indicate to me that I'm doing vector addition. This is why I wanted to put my vectors into component form, because when I do vector addition, massively easier to do that with the vectors already in component form. So I have both those numbers on my calculator already, so I'm just going to go and pull them there. So that's my x component. This would be my y component. So 5.1, negative 222.5. So far, so good. And that should make sense to the picture I've drawn, right? I have an answer in the fourth quadrant that's just barely crossing the y-axis, but way far down there. So that looks exactly like what I drew in my picture, so I feel pretty good about what I've done so far. Now I'm going to compute the magnitude. The formula for magnitude, if my vector's in component form, is, now it's time for the square root. And it's just the x component squared plus the y component squared. That's letter supposed to be an R. It got kind of V looking. So again, I'll just do that on my calculator. So I got 222.5. And I probably should say nautical miles. I think a nautical mile is technically different than like a mile on the ground. Not a ship captain, so I don't know for sure, but I think there's some kind of difference there. Everybody okay with how we got the magnitude out of that? Now we need the direction. So if I think about this, R is down here at the point like 5.1, negative 222.5. And we want that value, right? So just like we did in first semester, I'm going to draw my angle alpha. Between the terminal side of my angle and the x-axis. And I know then that my angle theta is going to be 360 minus that alpha. And we always find that alpha the same way. Tan inverse absolute value of y over x and because I'm going to steal the values here, I guess I will do the absolute value on my calculator. So I get 271.3. So that's my direction to go with my magnitude. So this is a lengthy computation, right? But it's a really excellent review of all of our things that we've done in 8.1 and 8.2, where you have to convert between your different vector forms, you have to add vectors, you have to convert back once you're in a component form back to a magnitude and direction form. So it's a really nice problem to review the things we did in 8.1 and 8.2. That feel okay what we did there? Tried to go slow and be pretty careful and explain what we're doing and draw a lot of pictures. Not all of it is 100% necessary, but I think it really helps understand what it is you're doing and where you're trying to get to and why you're doing the things that you're doing. If you have a nice picture and maybe if I over-explain things a little bit. Okay. The other idea here is we're going to introduce a new vector operation called a projection, and we're going to use that then to do another type of story problem. So here's the idea. Let's say I have some vector u. And some other vector v. What a vector projection is asking is how much of u, vector u, is going in the same direction as vector v. Okay, it's basically asking if I were to break vector u up into some other vector that's in the same direction as v, and then plus some other stuff, right? Like if I want to take the number 5 and break it up into 4 and some other stuff, I can write 5 equals 4 plus 1, right? So that's the idea here. So if I do this, if I draw make a right triangle here, this piece here, we're going to call the projection of vector u onto vector v. And if I call this vector w, we can say that vector u is equal to the projection of vector v onto u plus w. So this is what I had stated before, where I can rewrite vector u as some vector in the same direction as v plus some other stuff. And the other stuff is that w. So that's geometrically what we're describing. That's what it's doing. So let's define now computationally how we actually calculate this projection. So for non-zero vectors u and v, the projection of u onto v, we denote as projection, P-R-O-J. Then I do a subscript v of u. And then this is a scalar. It's u dot product with v divided by the magnitude of v squared. And that's going to be times the vector v. Remember that the result of a dot product of two vectors is a scalar, just a regular number. The magnitude of a vector is just a scalar, it's a regular number. So this is just a scalar multiplication. Everybody okay with that idea? So notice that in the picture here, we're projecting u onto v, right? So the v I've drawn, I drew v like absurdly long. Sometimes v will have a length given to us in the problem, and sometimes it won't. in the cases where vector v isn't, a length for v isn't given to us, you know what we're going to do? Just going to assume that vector v has length 1, has magnitude 1. Mostly because it'll make make the calculation much, much simpler. More often than not, all we really want, or all that's really necessary, is just to have a unit vector in the same direction as v. So these couple of things that I've just dropped in here are just what we talked about. How if v isn't given to us, oftentimes we'll just assume the magnitude to be 1 and just find the unit vector in the same direction. And that coefficient, the u dot v over magnitude of v squared, is just a scalar. So this is really just a fancy scalar multiplication. All right, let's do some examples now on just computing a vector projection. Okay, it says to find the projection of u onto v, and then it says to do some other stuff, but let's do that part first. So there's my projection of u onto v. So we need to do u dot product v over the magnitude of v squared times vector v. So that's just me rewriting the formula with the vectors plugged in, right? Okay. How do I do a dot product of two vectors? What's the formula for doing that? So the dot product is the product of the x components, so 3 times 6, plus the product of the y components, 1 times negative 4. Is everybody okay there? In the denominator, then, we have the magnitude of v squared. How do I calculate the magnitude? It's the square root of the x component squared plus the y component squared. Is everybody okay with how I've used my formulas to kind of start picking away at this thing? 6 times 3 is 18. 1 times negative 4 is negative 4. 18 plus negative 4 is 14. Six squared is 36. Negative 4 squared is 16. So that's going to be the square root of 52, but notice that that's also squared. So like the square root and the squared can just kind of cancel each other off. Is everybody okay so far? All right. So this can reduce. I'm going to do that now. Yes, sir. Sure. So now go ahead and do the scalar multiplication. So I'm going to have 7 over 26 times 6 over 1, and then 7 over 26 times negative 4 over 1. Again, I noticed that, hey, I can do some reducing here. So that's going to give me 21 over 13, and then negative 14 over 13. So far, so good. Okay. And then the second part of the question says, then express the vector u as the sum of two orthogonal vectors, one of which is the projection of u onto v. What does this term orthogonal vectors mean? Do you remember from 8.2? Orthogonal means that the two vectors meet at a right angle, a 90-degree angle. So if we go back and we look at what we're looking for, we just need to figure out what this W is, right? Everybody's okay there? So I'm going to say, I can say U equals the projection of U onto V plus W. We know U, that was 3, 1. It was given to me in the problem. We know the projection of U onto V. We just calculated that. So we can solve this equation then for W. What do we need to do to both sides of this equation to get W by itself? I just need to subtract that projection vector to both sides, right? So to do this subtraction, I need to make a common denominator. So 3 is 13, or 39 over 13, and 1 is 13 over 13. So when I subtract this, I get 18 over 13, and then negative 1 over 13. That's my W. So now if I put it all together, I can say vector U is equal to my projection vector plus W. Oh my gosh, I made a mistake here. Did you see it, Tommy?
No, but that is restroom.
Yeah, I did make a mistake though. Who sees it? (13 over 13) minus a negative. Ugh, Mr. Kulik, that should be adding. Oops, what am I doing? 27. Oops, that was fine. Ay caramba, guys. So that's the second part. Sorry about the goof up there. Just opening a can of pop, it's okay. So far, so good? Okay. Let's look at some example of story problems where you can apply this idea of a vector projection. Okay. It says Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? So what we want to find is we're basically going to be projecting the force of gravity onto the hill. So I want to find what portion of gravity is going in the same direction as the hill. When you read that problem, can you kind of see that in your mind, right? Because what direction is gravity pulling? Straight down, right? We all live on Earth. That should be an easy question. Okay. If I'm on an angle, though, gravity isn't pulling me like into the hill per se. It's going to be, I end up rolling down the hill, sliding down the hill like on a sled. The reason I slide down is because gravity is pulling me. Now, is it pulling me? Am I going as fast as gravity down the hill? No, because not all of gravity is going in the same direction as the hill. Only part of it is. That part is the projection of the gravity vector onto the hill. Does that feel okay? So my first order of business here is to figure out what my vectors are, and I have two in this case. I have my gravity vector and my hill vector. Everybody's okay with that? The magnitude of my gravity vector is the weight. So that's the 165 pounds. Everybody's okay with that? And the direction for my gravity vector is going to be is the angle. So let's think about, here's our situation. There's my gravity vector. So the direction there is 270, right? From the picture I drew, we're going straight down. Does that feel okay so far? Okay. So to write my gravity vector then into component form, I'll do magnitude times cosine of the direction, comma, magnitude times sine of the direction. I get 0, comma, negative 165. It's a different color here. Does that feel okay there? You might have also just looked at the drawing we made of the gravity vector and go, oh, Well, the component form better be 0, negative 165. That would be fine as well. We only really needed the direction there to get the component form. But I wanted to like reinforce the formulas there rather than just like doing intuitive things that aren't really shortcuts unless you like understand what's going on and recognize there's a shortcut there. I'd rather do it the long way that works every single time than start throwing shortcuts at you when you just are seeing it for the first time. Okay, next up is I need to do the hill vector. So what information do we know about the hill? Only the angle of incline, right? All I have is a direction. Do I know anything about a magnitude, how long the hill is or anything like that? Guess what we do in these situations? Just going to assume the magnitude for the hill is 1. Right? Just like we mentioned before, that in the case where we're not given anything to indicate a magnitude for a vector that we're projecting onto, we can just assume that it's 1. Okay. Now let's think about the direction here. The direction is not 25 degrees, unfortunately. So if this is like my start, if I'm going down the hill, I'm doing like that kind of thing, right? And if it's an angle of incline, I know that that spot has to be 25 degrees, right? Because the arrow is basically like the bottom of the hill. So from geometry, I know that that little angle there is 25 degrees. So my direction should be 360 minus 25. So 335. So now I'm going to write my hill vector in component form. So magnitude times cosine of direction, comma, magnitude times sine of direction. Or I could just write it as, use the unit vector formula, which is just cosine theta, comma, sine theta. Any questions so far? Now that I have G and H, I'm going to calculate the projection of gravity onto the hill. So just like before, I'm going to start by just plugging in my pieces. Oops. And I could have at the previous stage like typed sine and cosine of 335 into my calculator and put a decimal there. But I don't need to do that. I'm just like, I'll just do it once when I need to do it. I don't need it yet. And remember, the magnitude for H is 1, so I'm not going to actually plug the component form into the formula. We chose that magnitude to be 1, so I'm just going to write it there. Yes, Thomas. Sure. Go ahead, Thomasino. So far, so good. Questions yet? We're okay, following along? So to do the dot product, what's the formula for a dot product? It's the product of the x components. So 0 times cosine 335. It is too messy. Plus the product of the y components, negative 165 times sine 335. Now notice this piece, 0 times anything just is 0. You can ignore that. So basically I have negative 165 times sine of 335, and I have to multiply that into cosine 335 and sine 335. So negative 165 times sine 335 times cosine 335. And then that same thing, but it's sine 335. So 63.2 and negative 29.5. So far, so good. And so my last piece is going to be my force, is going to be the magnitude of that projection vector. And again, the magnitude is the square root of the x component squared plus the y component squared. So into my calculator this all goes. And I get about 69.7 pounds. Now you're saying to me, Mr. Kulik, that felt like a lot, right? Now, I want to point out to you something, because there's actually an earlier exit option to this problem where we could have gotten away without having to do all of this for this particular situation. So let me pick a color I haven't used yet. Okay, so let me go back here. When we make this assumption, the magnitude of H is 1. My answer for force is just going to be the absolute value of the dot product for H and G. In other words, It's the absolute value of that number. You can skip doing all the projection nonsense and all these other things. Now, the $10,000 question is why? So if I'm doing the magnitude of the projection of H onto V, that's the magnitude of H dot G over, well, I'm going to write the 1 squared there, times H, right? Now, H dot G is just a scalar. So I can like take that scalar out with an absolute value. And then I just have that scalar times the magnitude of H. What's the magnitude of H again? We decided it to be 1. So we're just left with the absolute value of H and G. So in a problem where we can select the magnitude of our projection vector to be 1, all I need is the dot product of my two vectors. That's all I need. Is that okay? Nice little shortcut. But it's only available if I'm allowed to choose the magnitude of my vector, my projection vector, to be 1. Okie dokie. All right. Let's do one more example, and that'll finish us up, I think. You guys look all pretty cooked at this point, but I have one more example here on my list, and I think we can probably be a good idea to do it. Okay, it says a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assume that the crate is of negligible weight. What is the amount of force directed up the ramp? So in this question, there is no gravity vector. What part of the directions tells me that there is no gravity vector? The crate is of negligible weight. If the crate doesn't weigh anything, does gravity act on it? No. If it did, if it did have a mass and gravity was acting on it, then I have 3 vectors going on, where I'd have to add 2 of them and then project the sum onto the ramp. Here, because the crate has no mass, we don't have to do that. It's an imaginary crate. So when I read this, I see 2 vectors. I have the pull vector and the ramp vector. Everybody's okay with that? So the pull vector, I think pretty clearly the magnitude is going to be 100. And if I think about the picture of what we're doing, we're doing that, right? We're pulling it up a ramp, Everybody okay with that idea? So the direction there is just 40 degrees. As opposed to sliding down where it had to be in the fourth quadrant, right? In the previous problem because we were sliding down the hill. So my vector P is going to be 100 times cosine 40, comma, sine 40. So what do we know about the ramp? We just know the dimensions, right? So it tells us that we go 10 feet this way and 2 feet that way, right? On the ramp. Guess what that tells me? That's my component form. I don't need a magnitude, don't need a direction, because I only needed that stuff to get the component form anyway. It's just telling me the component form for my vector in the problem to try to save me some headache. That's a nice thing. We like that. What's the downside, though? We don't get to pick its magnitude to be 1. So we're going to have to do like the full problem like we did last time. There's no shortcut to exit. All right. So we need the magnitude of the projection of P onto R. So that's going to be the magnitude of P dot R over magnitude of R squared times magnitude of R, or times R. So I'm going to go ahead and compute 100 cosine 40 and 100 sine 40 here before I get going too far. I guess I probably want those as decimals as opposed to having to do all that extra writing. So 76.6 and 64.3. All right, 10 squared is 100, 2 squared is 4, so the bottom is 104. The square root and the squared cancel each other out. And then we have 10 times 76.6 plus 2 times 64.3. So that's 894.6. I have that times 10(2). Now, I'm going to do this, I'm going to do that and just break that up because I already did the magnitude of 10(2) before. So it's like 894.3 over 104 times the square root of 10 squared plus 2 squared. I'm going to take this over 104 and multiply it by the square root of 104. And I'm left with 87.7 pounds. That'll do us for today. So Sunday at midnight, the last Sunday, you should have finished for me 1 through 14, I think, right? For this Sunday, I had already assigned 15 to 40. And I'm going to assign new for this Sunday, 41 through 50. Again, expect this week, homework quiz covering sections 1 and 2. On that day that we do the homework quiz, I'll also have a Delta Math assignment for you to practice some of that 8.1 and 8.2 skills as well.